Well, thinking about math, to get a little outline here on a Saturday, I'm kind of work it this way so I don't bog down on one topic. I'm going to look at 4 different areas. We're going to play with numbers a little bit and do some calculations. And we're going to talk about the design that you see in mathematics. I got to talk about some of the pioneers, these men and women of faith who did all this math before us and made the discoveries. And then I have another area of anticipations. I'll tell you more what that means as we go along. And in fact, I would kind of like to cycle this through. And I'll look at each of these 4 ideas, then I'll go through and look at them again. And I have about 3 cycles. So we'll look at 3 calculations, we'll look at 3 design examples, we'll look at 3 wonderful mathematicians, and then 3 anticipations. At least we'll see if we can get through this. So if you're following, if you're outlining, if you're taking notes, that's kind of our plan. So we do have to do a little number stuff, so we got some calculations. So I'm going to start on the first one here as I'm going through this cycle. And the first question I'm going to have here, this just all relates to our creation worldview. Are there aliens? I mean, don't you wonder about this? The movies, everything is about this. Is there life in space? Of course, this is a major drive of NASA, and it's kind of irritating the way they're always looking for life, but I thought this would be a good place to start on a Saturday morning. So there's the question. Now, when you read the newspapers about this, and I love space research, all the pictures they're taking and all the probes, they always end up saying, you know, maybe we'll find life out there. In fact, I see this formula in the media. There's this grand assumption that if we can find another planet out there in space, and maybe there's water out there, and maybe there's an energy source, sunshine, then if you let enough time go by, life will show up. This seems to be a modern formula that they just assume works, and I want to say, I don't think so. It's not that simple. To get life, you don't just add water. I mean, as you know from your biology class, high school or wherever, a cell, the DNA, incredibly complicated. We haven't begun to know what's down there on those micro levels. So nice try, it doesn't work. Anyway, people work on this kind of thing, and since they haven't found any life in space, they calculate how much there is out there. So I wanted to, here comes a little bit of math now. There's something called the Drake equation. Now here's the fella, Frank Drake, has spent his whole life thinking about aliens. Now I don't put these guys down, very intelligent. He's, you know, advanced degrees, had a lot of time at the universities in California, and but his whole life in this business. And he's come up with what's called the Drake equation. So no quizzes on this, but here's our first calculation. So he's going to figure out how many planets have life on them in the Milky Way galaxy. Now that's our own galaxy, that big spiral, that big whirlpool. And here's his formula. There's different ways to write it. There's his picture. He's kind of elderly now. Here, let me define what those letters are, because I want to look at this with you for a minute. He's going to calculate how many planets have evolved life. So he begins with a little letter N, which is the number of stars in the Milky Way. Nobody knows, but we can estimate that. Stars in a galaxy. Then he has some fractions, F sub P, the fraction of those stars that have a planet. Because you can't live on a star, they're too hot. You have to live on a planet that's circling a star. The next fraction is the fraction of those planets that are solid, that are Earth-like. Because if it's a big gas ball, you can't stand on it, so you need to have an Earth-like place. And then the last fraction, F sub L, the number of those planets, the fraction where life has started, the Drake equation. Isn't that great on a Saturday morning? So he writes whole books on this. So then the next thing you need to do is put in the numbers. And that's where the guesswork comes in. But let me show you what's typically done. And it kind of looks like this, just to get the numbers. The stars in the Milky Way, it's somewhere around 100 billion. We'll accept that number. That's a typical number for any galaxy. That's 1 followed by 11 zeros. It's a big number, but, you know, a ballpark figure, 100 billion. That's little n. Now, the fraction of those stars that have planets, I mean, the sun is one of them, and we know we have planets, but how many others? And they're finding some new planets these days. Just to be conservative, typically you put in 0.1. Maybe 1/10 of those stars have planets. Get the idea? Okay, then the next fraction. How many of those planets have a solid surface like the Earth. They put in another 0.1. Now, the last term is always quite optimistic if you have that kind of setup where life will start and they put in a 1. And there's the result. The conclusion, there must be 1 billion alien inhabited planets in the Milky Way. Isn't that a great calculation? Now, I know it's early on a Saturday morning, but you're looking at this. Is anything suspicious in this list? If you were talking to Dr. Drake, would you say something? What would you say? Thank you. You're looking at these numbers here, and yes, if you're following it, no problem with 100 billion, and those 0.1s may be okay, but that 1, really now, if things are just right, life will start up, evolve life, it needs to be challenged. Now, this is typically what's published, but let me correct this a little bit. Here's the truth. The chance of life evolving on a planet is nada. It's 0. That's what all of our experiments show. The last term is a 0, so the other numbers don't even matter because you're multiplying by a 0. Here's the real answer. Planets with evolved life, none at all. They don't like that because they like to get these big numbers, but there it is, and I think that's more truthful. So anyway, that's an interesting calculation. And by the way, I think we can also get a little help from our Bible basis for this whole question. There's that question again, is there life in space? When you turn to Scripture, here's Psalm 115:16. The highest heavens belong to the Lord. It's the earth he gave to us. It's not the residence of aliens out there. That's God's world. Now, I know there's a spirit world out there, but we don't find anybody else. In fact, you know what astronomers are saying these days? Where is everybody? If there are so many inhabited places, they should be all around us. It looks more and more, folks, like we are unique, like we're special, and I think that's the biblical way. Now, let me say, if they do find life in space, maybe on Mars or someplace, like microbes, we probably put it there. We've sent enough probes out now. We may have contaminated our near environment, but as far as evolved life, I don't think so. Nice try on the Drake equation. So we're moving along here through this cycle. The next thing we wanted to mention was a little bit design in mathematics. I was just looking at some fossil ammonites here. Aren't they beautiful? These kind of shells, so interesting. And I was thinking of spirals, this whole pattern, as an idea of design in nature. Now, as you know, in the math world, there you can fit formulas to this, and I don't want to do a lot of math this morning, but there's the equations that describe a spiral, and it goes around and round. In fact, it seems to be a shape, a design that the Creator likes, because there's lots of spirals around us. Here's some more pictures. Some of you know what this is. The little picture on the left, it's a seed called a filary, and it grows in Arizona. It's a weed. And there's a little seed on the end. It looks like a fish hook or something. But this is the most interesting seed that grows in the wilderness. The plant blows these seeds around, and then the seeds are self-planting. They spin and drill themselves into the ground. We don't have any corn like that back in Indiana that plants itself. But these seeds, since there's nobody out there to take care of them, God programmed so they plant themselves. And on the other side, there's a picture of a climbing vine like we have in our yard. Spirals, they're all around us. Here's another one. Now, that's a Calla Lily on the left. They came in different colors. And on the right is an interesting device that's been built based on the shape of a Calla Lily. It's called a lily impeller. And I like these ideas where they take things from nature and then come up with products. Now here is again a shell and another lily impeller. And there's a little kind of a story that goes with what I'm showing you now. It's looking at nature, seeing this spiral shape, and then using it to solve problems. So anyway, there's an inventor. His name is Jay Harmon. He was in Australia. I think he's in the U.S. now. And he has this company called Pax Technologies. And he got to looking at these spirals and thought, you know, this might be useful. And so he makes these metal spirals. They look like an auger. There's the picture on the right. And he has found out that this shape is just what you need to keep water moving, to stir water in water tanks, and big vessels. And he makes these little devices. They're only like 1 foot high. And as he turns those with a little motor, he can keep circulating hundreds of thousands of gallons of water. And now he's taken this shape and he's using it to build, it's going to replace propellers on airplanes. And it can be used as a pump. And they're going to build big ones outside to blow the fog away in airports. They're getting all this idea from this shape by looking at shells and spirals that God made in the first place. This is great stuff, looking at design in nature. In fact, I got to tell you, I'll be back to the math in a minute, but a while back, one of my students and I'm back at Grace College, we put this book together, Discovery of Design. And in this book, there's some on the back table there, we have about 100 examples like this where something from nature is used to solve a problem or come up with a new technical product. I think that God's put endless ideas in nature for us to find and make use of for our better living. In fact, let me keep on going here for a minute and just show you another one because I like this idea of intelligent design. You like spiders, don't you? Maybe not, but we can learn from spiders. So there's something about spiders that I wanted to mention to you. And now I got to connect this, if you can follow me, with birds. There's a bird flying around through the air. Have you ever heard a bird smacking into a window? I don't like that sound. You know, either they think it's open or they see a reflection and think that it's just open territory and they hit it. And sometimes they survive and sometimes they don't. Well, back to these spiders. Very seldom will a bird get tangled in a spider web. They avoid them, and spiders don't want birds in their web. They want bugs, not bigger things like that. So they've studied these spider webs to see how is it that they repel birds. What we have found out is that some spiders, they coat their web with a film of material which reflects ultraviolet light. Now, we can't see that kind of light. It's black light, it's ultraviolet, but birds can see it. And so they avoid hitting the spider web. So even in the dark, you might not see a spider web, but to a bird, that web is lit up and tells them to stay away and avoid it. Kind of a neat idea. Those spiders are pretty sharp after all. So this idea, right during our time here, is being applied to windows to protect birds. They're taking these large office windows and they're putting strips of this material on it that reflects ultraviolet light. So when the bird's coming at it, he sees, like the picture on the right here, he sees all these lines so he doesn't hit the window, whereas all we see is an open, clear window. Ideas in nature, design that God put there, and now we're even having spiders teach us how to protect birds. It's a whole new way to look at science, looking at what God set up for us just to, live better and even care for the creatures. Hey, we're going through some math here, and on this first cycle, we got to talk about a mathematician also. So here's Leonhard Euler, and here's a picture, at least on a postage stamp, a fellow who lived some time ago in Switzerland. Just going to tell you a little bit about him, because he's the kind of guy who set up the math that we all enjoy today. He lived 3 centuries ago, one of the greatest mathematicians of all time. He wrote over 70 books. And this is before word processing, before computers. And he was blind the last 2 decades of his life. How did these people possibly do that? By the way, on this, beside that stamp there, I have what's called the Euler identity, one of the most famous equations in all of mathematics. It's got in it little I, that's the base of the imaginary numbers. It's got E, the base of the logarithms. It's got pi in it. It's got all this good stuff. Anyway, Euler and his wife Catherine had 13 children. Not all of them survived. And when you read the biography of this guy, it says his family and his faith were his greatest joy. I like these examples. If you like creation, you got some wonderful men and women to follow and learn from. Euler was a man of God. He believed that math was the language of creation. And it is. Maybe some of us don't like math very well, but Euler did and God did, because it's all around us in mathematics. So again, we're going through this first cycle, and so that was the idea there on a mathematician, but we got to keep rolling here. By the way, the quotes that Euler made are kind of interesting. Now, you don't have to take notes on this, but I like the way that this guy wrote, again, with these 50 volumes that he had. Look at this note from one of his books. For the sake of brevity, let's represent this number, blah, 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 by the letter E. I mean, it's kind of comical the way he wrote. I'm sure he had that number there, the base of the natural logarithms memorized, but he came up with this idea of little e that's all around in mathematics now. Reading these classics from the past from these people are just fun to look at. Well, now in this first cycle, that last thing we want to look at, I called it math anticipations. And what I mean by this is over and over again, they'll come up with some new area of math that they study. They'll do a new function, a whole new area. And people will say, well, that's interesting, but what's the use of it? And then later on, they all of a sudden find that it shows up in nature. It was there all the time. So as an example of a math anticipation, here's a complicated picture of an ellipse. Remember what these look like? A squash circle? Looks like a doorknob or something, or maybe an egg. Anyway, the mathematics of an ellipse was laid down way back in Greek times. So you're back there in New Testament times, 2,000 years ago. And it was good mathematics, kind of elegant, but there it sat until about 1,500 years later, the time of Johann Kepler, when it was realized that this is exactly the kind of math we need to describe the orbit of the Earth around the sun. We knew the math before we realized where it fits. This once again shows that math is embedded in nature. It's the language of creation, and sooner or later we find out where it fits after all. Anticipations. You had the math before you found out where it really existed in nature. There's other examples of this. There's another one called Maxwell's equations. This is Clerk Maxwell, who came up with these fancy equations. There they are on a T-shirt, and that goes back to the 1860s. And then about 20 years later, it was realized that, yeah, those are just the formulas you need to describe light and ultraviolet light and radio waves. The math came before it was realized it was there all the time in nature. By the way, the people that did that second one there, Maxwell, that's another name of a good creationist from the past. Let me put two pictures on the screen. These two guys here, they would give a good talk at a conference like this. They were godly men. They were men of faith, and they were also gifted with great intellect by their maker. First of all, we got Michael Faraday. You've heard that name before? The greatest inventor of all time. He never went to school. I mean, he was homeschooled at home, but he never had a lot of opportunity. A poor family in England, but he had great insight, and he was an experimenter. He made the first motor, the first generator, the first battery. He did the first lots of things. Then along came his friend Maxwell, remember the Maxwell equations, who was educated and had all the theory to put them together, what Faraday had come up with. So anyway, two great examples right here of pioneer mathematicians and scientists, almost every one of them with wonderful testimonies. Hey, we're moving along here. So snowflakes. Now, I'm kind of slipping into the next calculation. We're on to our second cycle. But I wanted to start with this. And just to keep us awake here on a Saturday morning, I got a couple pictures here. Snowflakes. Do they actually have 6 points or 8 points? Look at it a minute. Can you turn to your neighbor and see which one you agree? And then we'll get the answer. What are snowflakes like? Because they're all pretty much the same. Which one do you like? Can you get your answer from your friend? And then we'll see if you're right or not. But we're going to keep moving because we're behind schedule here. Well, 8 points or 6 points. Now, I know they can be broken, they can be half melted, but the way, the covalent bonding works for these things, and the answer must be 6 points, because people specialize this and take these cold temperature pictures of a snowflake. So there it is. Snowflakes are wonderful. I know you don't get a lot of it here. There certainly was some snow up there in Mount Rainier, and we get it back in the Midwest. Now, you have heard that every snowflake is different. Who comes up with an idea like that? Is that possible? I mean, back home, our whole driveway fills up with snow, and year after year, and since the beginning of time, and you say, well, I've seen two snowflakes that look alike. Can they all be different? We better answer that question, because that involves math. It is true that every snowflake is unique. there are no two that have ever been identical. And let's take a minute and prove that, because that involves mathematics. So we'll take a quick shot at that. Now, let me back up, first of all, thinking about these snowflakes. Suppose that we had a baseball team. Okay, here they are, guys and gals lined up on our platform. 9 people. Okay, they're going to pose for a picture. They're just going to stand in a row, 9 people. How many different arrangements could there be for 9 people to line up for a picture? You could get different ways, you know, from the tallest down or whatever. So the first person walks up and he's got 9 different places where he can stand. Well, then the next person walks up and he's got 8 different places where he can stand. Here, in fact, I have a picture of the baseball team right here. It's the best picture I could get, but I think I got 9 of them there. The next person has 7 places. Now, you know how many arrangements there are with 9 people? If we had 9 of us come up here and we were going to take every possible arrangement, we would be here for the whole weekend. Because to figure this out, you got to take 9 times 8 times 7, all the way down to 1. This is called 9 factorial. They use that exclamation point, and there's over 300,000 different ways. Even if you got fewer people in that, the number goes up in a hurry. So you could never do this with a baseball team. You'd be at it a long time. That many different ways that 9 people could line up. Now move to a snowflake. You don't have 9 people, but you have lots of variables. Sometimes one of the points of a snowflake is gone. Sometimes there's an impurity atom in a snowflake, an atom of carbon or an atom of silicon or something. Sometimes there's a little chemical defect in the snowflake. I'm talking about variables now. How many different things could happen in a snowflake? More than 9. In fact, let me guess that there's 100 different things that could happen. Again, these are called variables. Throw an impurity atom, change one of the chemical bonds. And so when you're thinking about snowflakes, if you have 100 different things that are going on, to figure out how many different snowflakes there could be, you need to take 100 times 99 times 98, all the way down to 1. Should we haul out our calculators and do that? I don't know if there's a shortcut, but it's going to be busy for a while to do that. It's almost like a whole stadium full of people, and if 2 of them change position, it's a different arrangement. Maybe snowflakes look the same on the outside sometimes, but on the inside, microscopically, that's where the differences show up. So anyway, I was trying to figure that out here, and if you do 100 factorial, it's over 157 zeros, a number beyond the number of atoms we know of in the universe. And so the probability that 2 snowflakes would be identical, even on the inside, is 0. It is true that every snowflake is different. Likewise, every grain of sand is different. Every kernel of corn, every blade of grass, certainly we're all different. Every raindrop is different because there's not the same number of... Isn't that what creation is like? It puts us in our place, and God keeps track of it all, and so there it is. Amazing. So anyway, that was our second calculation. Did we prove that all the snowflakes are different? It works. Now, our next area was design, as we're going through this cycle. And so have you run into Fibonacci, Leonardo? Now, this guy lived centuries ago. He was a mathematician, and he also liked nature and playing with numbers. So we got to talk about Fibonacci numbers. There's a whole Fibonacci society among mathematicians. They like this guy. Now, here's the kind of thing he does. He takes some numbers, and he writes a pattern. So here's the pattern we got going. I know the writing's a little small, but I can see it. He goes 1, 2, 3, 5. What do you think the next number is? Maybe there's more than one pattern, but he's using one. Anybody know what it is? I hear the number 8. We got some Fibonacci people here. What's the next number? 13. Some of you are saying, I don't need this on a Saturday morning. You're giving me a headache. What we're doing is taking the 2 previous numbers and adding them together to get the next number. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8, well, this keeps on going, and we got to keep going ourselves here. The numbers kind of get big after a while. They're called Fibonacci numbers. And there's a whole journal dedicated to these numbers because they're very special. And what Fibonacci found out is that these numbers show up in nature with unusual frequency. In other words, there's a lot of flowers that have 8 petals or 13 petals. There's not very many that would have 7 petals or 9 or 10 petals. Now, there's exceptions, but these numbers seem to just dominate. And let me show you a couple more examples of this. A 3-leaf clover. Now, remember going outside in the summer and looking for a 4-leaf clover? Can you find one? You know, good luck. Well, you can find a 4-leaf clover, but that's a mutation. That's a mistake. Clovers come with 3 petals, and 3 is a Fibonacci number. 4 is not. This little deal on the right here is a sand dollar with a 5-pointed star. 5, a Fibonacci number, so this shows up in the animal world. This really gets interesting with the bigger numbers. Here's a sunflower. And if you can look carefully at the spirals in a sunflower and count the number of spirals, you'll get either the number 34 or 55 or 89. You'll get these Fibonacci numbers. Try it sometime. Or the spirals on a pine cone or on the outside of a pineapple. It's always Fibonacci. Anyway, it's an interesting design in nature that these numbers seem to be preferred. They seem to dominate. Now, what am I saying? What is this stuff? How come these numbers? You know what I think we're looking at here? God's fingerprint. He likes these patterns. And this is an intelligent pattern where you're adding numbers together. And so there it is. And the biology world has never come up with a good explanation for this, why these numbers are so dominant. But they are. They're there. And it's good stuff. Design in nature. I got to keep moving with my cycles here. So we got to bring a gal into the story this time. So now we have Maria Agnesi. And you can see that she lived a long time ago as well. Let me find her little note here since we're talking about people. An extraordinary lady who lived in Italy. By the age of 10, she had mastered French, Latin, German, Spanish, and Hebrew. I mean, the way God's gifted some of these gals and guys is just amazing. She was the oldest of 21 children. She learned math from her father, who was also in mathematics. And during her early years, she overlapped with Isaac Newton. She was living during that era. Anyway, she had a strong, conservative, Catholic faith. And later on in life, she began helping the sick. She became known as an angel of consolation. She lived with these sick people and cared for them. And when she died, she was buried alongside these people that she had cared for. She had an outstanding math career and a life of Christian service to others. And she also wrote one of the first calculus books. It's called Analytical Institutions, but that's what she did because she was doing math along with everything else. Here's what the cover of her book looks like, and there's one of the functions, one of the formulas that she worked on. It's a graph over there on the right. By the way, again, just to keep us awake here on a Saturday morning, I was reading the fine print at the bottom of this book. That's the cover that she wrote, and of course they put the publication date in Roman numerals. Remember the Roman numerals? Look at that a minute. What year did they publish this? Remember how this goes? You got the M and the D and the C. Try it out a minute. See if you can come up with it. We're keeping awake this morning. I know that the M is 1,000, and the C's are 100. I remember that. I got to put the answer in because it's got to keep on rolling. 1748. Did you get it? That's when this book was written. When all this math was first being done, Newton and this gal, Miss Agnesi, figuring out the beginnings of mathematics, of calculus. Well, now the other thing we had in this cycle was the anticipations. Remember that? Where they get the math and then they find out that it fits nature after all. So here's another example or two. The whole world of matrices, which is very valuable and takes computers to really solve these things, that was set up back in 1850, and matrices were interesting, but it was just an area of pure and useless mathematics until the whole area of flight and aircraft where these things are used to design airplanes. I like one of these early pioneers who was making use of matrix theory, Olga, who said, I didn't look for matrix theory, it found me. In other words, this pattern was there in nature to help build better planes. It was there all the time, and she's made good use of that. And by the way, here's another example. I'm kind of doing these twos, these anticipations. This fellow by the name of George Boole, who's living back in the 1800s, he worked with binary numbers, the 1 and 0, the digital type stuff. And that's a whole area of math, but it was just kind of just pure math, kind of useless, and it sat there for a long time. Then during our lifetimes here, with the whole electronics revolution, everything runs on digital now, switches, solid state, off and on, and suddenly it was realized Boolean algebra is just what we need. And it's been sitting there on the shelf for decades. So these things, sooner or later, come to be very useful. In fact, here's a classic article at the bottom of this picture. And if you're into math, you might like to just put in a few of those words, and you'll find it on Google, because it's everywhere. And it's kind of a long article. But this mathematician, Gene Wigner, you can see the title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. These wonderful math patterns that we find, even if we don't know what their use is at the time, sooner or later it becomes valuable to us. Okay, I hope you're staying with me here. We're doing some math here this morning. We're already up to the third cycle as time is going on here. So we're back to another calculation. And remember, we've had 3 of those. Whatever the first 2 were, I've forgotten them already. But this time I'm thinking of, I got the seashore here. I got some sand. And actually what I'm thinking of here on this third calculation, I'm thinking about space and how many stars there are. So maybe you could help me with this. Let's think about how many grains of sand there are on all the seashores of the whole planet. You say, well, lots of luck on that. But we can estimate this. So work with me on this. Suppose that this platform is the seashore. So you guys are the water. So here we are. So we've got a whiteboard here. So let me do this to kind of help. Let me just kind of sketch this. I'm going to make this real simple here, but I'm thinking of a beach, and I know waves all around, and we got Great Lakes, and you got the ocean. But let me just draw something here. I'm going to kind of take the seashore, and I'm going to say that the sand is about that thick, and the seashore is from the water is to where your parking lot would be, and then you got the length of the seashore. So let me just finish this off here if I can. Okay, I'm just trying to draw a big rectangle. Okay, can we let this represent the seashore? I think maybe you curve that a little bit more. Okay, so this is all sand. Now, some seashores have sand, some don't. Some are rock or whatever, but here it is. Now, here, let me do something else. Suppose you could reach out in the sand and pick up a handful of sand. Maybe make it a cube, like a little dice, 1 inch on each side. So here's my little 1-inch cube. Okay, if you would do this and even put some sand on a table and count the sand grains, let's say along 1 inch, let's make that 1 inch. How many sand grains could you line up? 1 inch. Just kind of take a little tweezer and put them side by side. We do this in class. I make them count sand grains. And we come up with a number, something like 100 sand grains could line up in 1 inch. So here's 1 cubic inch of sand. I got 100 sand grains this way, and 100 this way, and 100 this way. So if you had 1 cubic inch, how many grains of sand are there? Here, I'm going to write this down here. You would have 100, and you know how a cube works. It's length times height times width, so this is going to be cubed. That's 6 zeros. That's 1,000,000 sand grains you can hold in your hand. I mean, don't check it out. You can't count them. It's all estimates, but it works. Okay, now, I'm back to the whole seashore. Now, I'm going to put in some numbers here, and I think I have to guess at this. I'm going to guess that the depth of sand on a seashore goes down, let me put in 10 feet. Because some places there's no sand, other places there's lots of sand. So I'm going to put in 10-foot thickness average of sand on the seashore. Will you buy that? Boy, especially around the Great Lakes where I live, some of the beaches, there's no sand at all. It's just rock. In other words, quite a bit of sand. So that's 10 feet. Now, how wide is a beach? Here's the water, here's the land, here's the trees, the parking lot. I'm going to put in, well, some shorelines are wider than others. Let me put in 100 feet. That's pretty generous. Remember, this is all sand grains. Now, here's the hard one. What's the length of all the seashores of the world? I don't know. I've never seen this printed all the way around the ocean, all the way around your local lakes, all the way around the Great Lakes. Let me be generous here. I'm going to put in 1,000,000 miles. Okay? Actually, that's 40 times around the circumference of the Earth. I think that's generous. Okay, now I know how many sand grains are in 1 cubic inch. It's 1,000,000. Now I got to figure out how many cubic inches there are here. I'm figuring out how many sand grains there are in the whole planet on all the seashores. You say, I don't care, I don't want this, but I can't quit now. Okay, here's the 10 feet. So I got to go length times height times width. So here's 10 feet, but I got to change it to inches, so it's times 12. Hey, if anybody's got a calculator on your iPad or whatever, can you keep these numbers going for me and get the result? Okay, now here's the width of the beach. It's 100 feet. Oh, I got to turn that into inches, so it's going to be times 12. So far, I've got the depth of the beach, I've got the width of the beach, and the volume is length times height times width. So now I got to put in that big number, 1,000,000 miles. So that's 1,000,000 miles, 1,000,000 miles. But I don't want to have miles, I want to have inches. How many inches in a mile? You had to learn that once. Here, yeah, let's go, thank you. Let me go with feet first, 5,280, and then in every one of those there's 12 inches. This is our result. Can anybody crunch these numbers for us? I know what the answer is because I did this before, but I'm curious whether I did it right or not. And then round it off a little bit. Can you see all that stuff? Because this adds up. And this would be an estimate of all the sand grains on all the shores of the world. So approximately equal to. Okay, I'll put the number down, but again, check this out. See if I did this right. And I got to look at, oh, I remember what my answer is. Okay, when you do this, got to round things off a little bit. It's, why didn't I just write this down in the first place? It's 10 to the 22 power. It's 1 followed by 22 zeros. If I didn't do that right, don't tell me because I think I got it correct. And that's what you get. And remember what we were doing in the first place, stars and sand grains? Well, that's cool. You got that on the screen. I like that. I could use your help more. Yeah. Anyway, that's the deal. That's what we came up with. And go ahead and click the next slide if we could then. And because I wanted to compare this with the stars. That's quite a number. In words, that would be 10 billion trillion. There it is. The number of stars that we have been able to photograph up to 2016 is the very same number. Presto. 1 followed by 22 zeros. Now, I just read in the news this week, they think there's another zero now, that it's 10 to the 23rd, but they haven't seen those stars. They're guessing. The conclusion here, folks, to this calculation, there are as many stars in the sky as there are grains of sand on all the seashore, including the sand in your shoe if you've been walking on the beach. Think about this, how many stars there are. You know, just this vast number. Interesting how they come out so similar. Now, I did have to tweak the numbers, but I think it's quite realistic. By the way, this little exercise we just did is written up in a book. I have a book, Astronomy in the Bible, and there's some copies. They have a blue cover paperback, and they're kind of over there by the book sale table if you want to look at those. And my books are also available on Amazon, and they're all online as well, so help yourself. I do question-answer books, and that was one of the questions in the book, how do stars compare with sand grains? It's the same number. Very curious. Now, some of you can think back to the book of Genesis, where God is talking to Abraham, and he says, your seed will be as the stars in the sky or the sand on the seashore. That doesn't mean there's that many sons of Abraham. It just means you can't count them. And that number is still growing, and we're part of the whole story. So, yeah, well, I'm glad we got through that little exercise. No more math calculations here. But we got to keep moving, so I'm up to design. We're on this third cycle, so we're in the home stretch. I had to mention dogs. It has been found out that dogs know calculus. How do you like that? Some of us had to take calculus twice to get it straight, but here's the story here. Let me show you how this works. This comes from an article that was written by a fellow who teaches over at Hope College in Holland, Michigan. Anyway, this fellow was on the seashore on an afternoon not the seashore, by Lake Michigan. Let me see if I can, I don't know if this pen will help here. So here's this professor. He's a mathematician. His name is Tim, and he had his dog on the beach. And he was throwing a ball out in the water so the dog could go out and get it, summertime, Lake Michigan. And so there stands Tim, and he throws the ball way down the beach and out here in the water. And then his dog, Elvis, has to run into the water to get the ball. Now, how does this dog retrieve the ball? He has some choices. So the dog started out here next to Tim. The dog could have just jumped right into the water and swam, and got the ball like this. But, you know, it's slow going in the water. You can't move very fast. That would take longer. It's the shortest path, but the water kind of slow. Now, the dog could have also run all the way down the beach, run, and then go straight up to the ball. That would be the longest path. What he noticed, this professor, when he did this over and over again, the dog would run down the beach a certain length, and then he would take off and go through the water at a certain angle. And he studied this, and he made the measurements, and found out that what this dog was doing was taking the minimum time to get to the ball, partly on land, partly in the water. This is a calculus problem to minimize the time from one place to another, where first you're on the land and then in the water. So anyway, he wrote this article and said, my dog knows calculus. He knows how to find the minimum time, and he does. And I don't know if that comes by experience or what, but I thought, what a great example of design and nature. God even has programmed animals so they don't have to swim too much. And it's kind of become a classic article. I don't know if you followed that, but it's a calculus problem to minimize the time, exactly what the dog was doing in the first place. Good stuff. Good stuff. Anyway, we're on our third cycle, and here's our mathematician again. This time we have John Napier. So a mathematician and also a theologian. In fact, he's from Scotland, and he urged his country to maintain its biblical heritage. You can see when he's living, a couple centuries ago. This is the man who invented logarithms, and we see those on a slide, those on lots of other places. By the way, he says that he got this idea by studying horse tails. Some of you know this plant that's in this picture, which has different sections. We always call the Chinese puzzle, which you put them together and pull them apart, and those sections have different lengths, and it matches what is a logarithm. This guy also started the idea of a decimal point when it comes to mathematics. Anyway, it's another pioneer person in math, and used nature to come up with things like logarithms, so useful to us, and a godly man. One after another. We could go all day long with these pioneer mathematicians who have wonderful testimonies. And then anyway, we're down to our last anticipation here as well. And now I'm thinking of the sky. I'm thinking of space. There are certain kinds of stars that they blink off and on. They wink at us. They call them pulsars. And some of them are rather rapid. And that signal on the lower left there kind of shows the pulse signals that they give off. These are unusual stars. Their light comes and goes. How would you like it if the sun would do that? On, off. It'd be like a strobe light. It'd be like all probably pass out. Thankfully, the sun is steady. The sun is pulsars. Some blink 100, like 1,000 times per second. Anyway, what we think these pulsars are doing are small collapse stars, and they're spinning real fast. And there's this light and this radiation that shoots out of the blue part of these pictures. And if we're lined up just right, this flash comes by us, like a searchlight. We catch these flashes. And we've seen hundreds of these pulsars. Anyway, why would I bring this up? These are so regular. This pulse rate, the way they spin, that they become a time standard. They are more accurate than atomic clock. Now, in this day of computers, you need very precise time, satellites to keep everything running. And these kinds of stars are just a natural, like a quartz clock at the timer that they're making use of, competing with all those that they have as well. Then interesting scriptures are that stars are signs or seasons, and this way they're being used to keep track of the time scale on the tiniest amount. There's an article. There's an article a little while back where they're saying yes, this will be for the future. We need for the future. And then we get into nanoseconds, less another design idea. Ideas go on and on. Let me just take a couple more minutes. Sneak into a fourth cycle. I just got one you might be interested in this. This will be a cycle, and I'll be done. I got to thinking about this evidence for the Genesis using mathematics. And so I'll call this a foot. Now, population. You start with two people, Adam and Eve, and then the population starts 1,500 years. People wander back on God, goes crazy, cleans it up with water. Clean it up again with fire. Next time scriptures. Anyway, it all starts over again with Noah, and it would be 8 people. That would be 8 people. Can we go from 8 to the population today in biblical time? Some people would say nope, you can't do it. You can't do it. It can't be real. Some other story. So I got to thinking about. Let me try this. Here's some dates. I'm going to really exactly. Don't hold me exactly. We don't know exactly what creation was. God floods. I don't think God wants us exact. But these are ballpark figures. The Genesis flood. 2500 BC. Okay, that's my take on it. Creation, young Earth creation. It fits. Today, 2016. How many years go by there? 4,500 years since the flood. Rounding numbers off. Ballpark figures. Okay. Now, the Earth's population. It's growing exponentially. It's also called geometric. Every so many years, the Earth's population doubles in spite of wars and AIDS and terrorists and all this crazy stuff going on. It just keeps growing. And I know people die off, but the population is growing. In fact, at present, the Earth's population doubles about every 55 years. Plus or minus a couple numbers there, but about 55. This means those of us that have been around 50 years or more, we've seen the Earth's population double. When I was a teenager, there was 3.5 billion people in this world. Now there's over 7 billion. This is relentless. The way this population grows. That's why all these buildings are going up around Seattle and the roads are getting busier. It's double. And another 55 years, if the Lord permits, it'll double again. It'll go from 7 billion to 14 billion. And then to 28 billion. And then to 56 billion. Wow. By the way, there is room on this earth for those kind of numbers. There's enough air, there's enough food. Of course, people aren't very sharing, but there is great potential in this world. I got to thinking, if you have 4,500 years ago, people, in fact, maybe I'll start with 6 people. I'm not sure if Noah and his wife had any more children, but there were those 3 couples, their sons and their wives, and that starts to grow. And I was trying this and putting in some numbers. So I start with 6 people. There's Noah's 3 sons and daughters. And then after one doubling, you'll have 12 people in the world. This is taking off from the flood. And then 24 and 48. And this happens about 30 times. In fact, I'm even making this longer than 55 years. I spread it out a little bit more than that. I'm not sure if the population was going quite as fast then as it was today. So what do you do if you start with 6 people and you double this number 30 times? It's another math problem. This would be 6 times 2 to the 30th power. Okay, so this is since Noah. If you do these numbers, what you end up with is 7.4 billion people in the world today. What is the population today? It's that. This shows that by all means you can get to present world's population starting from Noah. This is just further evidence of the truthfulness of the whole reliability of Scripture story, including the Genesis flood. Again, I had to tweak these numbers a little bit, but this is all very conservative. Don't buy into this idea that we couldn't get here where we are today with 8 people. You certainly can. So there you are. You're one of them, all these people we have on the screen. Wow, we made it through our math and creation talk here with that different cycle. This goes on and on. I know we're not all into mathematics in a big way, but it is a wonderful part of creation, and it's on our side, and it supports what we're doing. So there. Thanks for listening, folks.